If we're using a fluorescent particle, we need to have some understanding of fluorescent light, or sorry, of black light and the light that's needed in order to make those particles show up really well. So when we're performing fluorescent inspection, the fluorescent particles, the fluorescent dye or coating that's on there, will glow under the presence of ultraviolet light. Okay? And we're going to use a very specific bandwidth of ultraviolet light in order to make them glow. You can use kind of a wide range of ultraviolet lights to do this, but the problem, there's a big problem with ultraviolet light in people. What's that? What can ultraviolet light do to you if it's too strong? Can blind you, it can burn your skin, right? It can cause sunburn. It's the same thing as sunburn or sun blindness. So, the further into the ultraviolet category we get, everything, here's at the top here is the electromagnetic spectrum. And we start with radio and microwave to the right. Okay, those are long wavelengths. And then infrared, which is heat. We experience it as heat, as people, as humans. We got this narrow band of wavelengths that we can see, that's the visible light spectrum. And then continuing on to the left, we have ultraviolet and X-ray and gamma. And you can see besides, kind of the visible light range, and maybe some of the radio ranges, a lot of this stuff isn't things you want to be in contact with all the time. Right? High amounts of infrared, we want a certain amount to keep us warm. Right? We can use infrared heaters, but we don't want to cook ourselves. There's infrared ovens and stuff like that. Radio waves, certain ones you got to be careful with, particularly in the microwave region. Again, we don't want to cook ourselves. To the left side, ultraviolet can burn your skin. X-ray can cause cancer. Gamma and X-ray actually work the same way. And cosmic rays, right? Those are all cancer causing. They basically destroy your body cells and your DNA. So, we don't want to be playing around with those too much, or if we do, we got to be real careful that we don't hurt ourselves. So when we talk about black light is long wavelength UV light. So here's our visible spectrum. We get into the purples, and then we get into ultraviolet. There's this band right here that our light transitions from visible to ultraviolet. That's the black light range. That's what we're looking at right there. And it is called long wavelength ultraviolet. Now, when I say long, you can see the ultraviolet as you go to the, right? But it's the far end of the, right? Because the longer wavelengths are over here with radio, microwave, and all that. So, they're the long wavelengths of the ultraviolet, X-ray, gamma ray side of the spectrum. And they are specifically in a range of, light is measured a few different ways. It can be measured in length. It can be measured in something called angstroms, which is just length times 10. So 3,500 to 3,800 angstroms, which is equal to 350 to 380 nanometers. So each wavelength, each up and down of the wave is 350 to 380 nanometers. Ideally, we look at the 3,650 angstroms or 365 nanometer range. So our light, what we have is with our UV lights we're using, they're a bulb. They're going to produce a certain amount of visible light. We can't make a bulb that just does a very, very specific. I mean, you can take a bulb, make the wavelength more and more specific by altering the chemistry of the materials in the, in the halogen bulb or in the LED or whatever it is you're using to generate light. But you can only get it down to a certain band, right? And it gets prohibitively expensive to try to get it, that light more and more pure at a certain wavelength. So the way our lights work is our lights that we have are going to be a little bit wider than this. They're going to give off a certain amount of visible light. They're going to give off a certain amount of ultraviolet light. And then what we do is we put a glass or mineral filter in front of them that filters out, hopefully filters out everything we don't want, or most of what we don't want, and tries to just let through things, a wavelength somewhere around 365 nanometers. Again, it's not going to be just 365 nanometer light because that filter is going to have a range, but it's a very narrow filter, hopefully keeping out the dangerous UV, most of the dangerous UV. Also, we don't want visible light because it makes it harder to see what we're looking at. So it's going to try to filter, those filters are going to bring it as close as possible to that ideal black light category, which doesn't appear as visible light to us, but doesn't also cause skin and eye damage. The other part about it we have to know is when we're working with these lights, we got to make sure we have a strong enough light that we're going to be able to see what we're trying to see. And so our light strength has to have a minimum of 1,000, 1,000 microwatts per centimeter squared. All right. I was talking nano, I had to switch to micro here. So 1,000 microwatts per centimeter squared at a distance of 15 inches. What that means is if we take our black light emitter, typically it's like a flashlight or a handheld light, and we hold it, 15 inches away, right? They like mixing units here. You can see we're using watts and centimeters, but then at a certain inch distance, right? We hold it at 15 inches away. We are going to measure that. We have to measure that to make sure our light, our torch, flashlight, whatever, is putting out the correct intensity, the amount of light, that it's bright enough that we're going to be able to see what we need to see. Now, when we're actually doing our inspection, oftentimes we'll put the light a little bit closer to our part if we need to make it brighter, if we need a more intense, but sometimes we also have to bring that light a little bit further away. Just like when you did visual inspection, too much light can be just as bad as too little light. So, and here I just have the visible light. So black light, 365 nanometers is only about 15 nanometers different from the top end of the visible light spectrum. Now, you and I and everyone else is going to have a slightly different visible light, top end, because it just depends on the cones and rods in your eyes and exactly what you can sense. So we're going to use this to view those particles. I've got some general guidelines in here for current. So when we run our parts in our process, we have to make sure we want to reach that saturation point. Remember, the saturation point is where all those magnetic fields in the individual atoms and crystals of the structure align. And remember, once the part's saturated, once we reach a saturation point, we can't make it any more magnetic. Right? Once all those individual little fields are aligned, that's as strong of a field as we're going to get. But if we exceed the amount of current needed to reach that, at that point, we're going to start heating the part up, and we don't want to cause heat damage to the part. So manufacturers and the engineers behind it and that kind of thing have come up with general tables that are going to be in the manuals for specific parts. So if you're working with a part and you're performing MPI, there's going to be a procedure developed that's going to tell you how much current you need for that given part. Here is an example out of, I want to say this is the 0470 overhaul manual. And it shows, for different parts, like a crankshaft, very large part, right? It can handle a lot of current. They're going to tell you, they want you to run 2,000 amps through it. Areas to be aware of, journals, bearing journals, they take a lot of abuse, right? So they probably have prone to cracking at bearing journals and other damage. Fillets, oil holes, thrust flanges, where the propeller attaches, right? Prop flange, right? So, and we're looking for things like fatigue cracks, heat cracks, flange cracks, prop strike. The other thing is if you're doing an engine, if you're doing one of these that sits around a lot, what else might we be looking for? Evidence of what? Rust or corrosion, right? Moisture gets in between the bearing, the journals, and the crankshaft bearings, or the journals and the connecting rod bearings, right? And then creates little moisture pockets in there that can rust the journal areas. So, looking at corrosion and that kind of thing. Connecting rods, they get a lot of abuse, fatigue cracking, that kind of thing. Camshaft, the lobes, the journals, right? So you can see the areas, but as we go down this list, a connecting rod is smaller than a crankshaft, so it's got less current, right? A camshaft is smaller diameter than a crankshaft, so it's running at 1,500 amps instead of 2,000 amps. That's your goal. That's what you want to get to. Oftentimes benches, especially like crankshafts, our bench cannot put 2,000 amps through a crankshaft. It can reach about 1,800. For our purposes, it works. We can see the cracks. Those that have already done a crankshaft the other day, you saw the damage to it. Right? It shows up really, that's probably the easiest one to see. But, so you don't even have to reach that, but typically you want to reach that current, or you want to at least get to it, if not slightly above it, but you don't want to exceed it significantly to a point where you're going to overheat the part. And overheating doesn't just mean melting. Overheating can be hot enough to alter things like the hardness, the heat treatment, the tempering of the material. It doesn't have to actually cause any melting or visible damage, but if it gets hot enough that the metallic properties change, that can be a bad thing as well. The other thing we have to be aware of is our particle concentration. So we're mixing up this bath. We have a carrier solution, and then we're adding these magnetic particles to it. And we want to make sure there are enough particles floating around in there or being distributed in there that we're going to be able to get good indications from them. And so we have to check the concentration level on a regular basis. So this is the amount of those ferromagnetic particles that are suspended in the oil bath. They need to be checked daily, or in some cases, if you have a real high production environment where you have tons and tons of parts being tested, you may check them more often. So you take a 100 milliliter sample, you put it in a centrifuge tube, you allow it to settle for at least 60 minutes, and you're looking for 0.2 to 0.4 milliliters per 100 milliliters of solution. And you need to record this. They're going to want to know. Now, the centrifuge tube looks like this. So we fill it to 100 milliliters, we let it sit, and the particles are going to go down in the bottom here where we can look at fractions 0.2 to 0.4 milliliters. And you look at how much settles after that 60-minute period. Here's another view of one, kind of showing that tip a little bit closer. And here it's showing 0.1, 0.2, 0.3 milliliters of particles that have settled out of this 100 milliliters of solution. Okay? Again, 0.2 to 0.4 is our magic number. If it's above it, the particles can obscure indications because there's too many of them. If it's below it, we may not have enough to stick to those magnetic fields and get a good indication. We're going to leave off there today.